All right, so if we're going to determine the formation constant for this reaction, we're going to have silver plus 2 ammonias is in equilibrium with this complex ion. So the expression is going to be complex ion and then silver and ammonia squared. So that's the value we're after. And the problem is, as a practical matter in the lab, it's difficult. It's difficult to determine the silver concentration or this one, right? Ammonia we can do. So what we've got to do is devise a setup so that the titration will give us something that we can quantify. That means we've got to use chloride ions. We've got to add chloride ions so that we can get a handle on what that is. That's the purpose of potassium chloride. The potassium chloride is 0.1 molar. The silver nitrate is 0.1 molar, which makes silver ions 0.1 molar. The ammonia is a little more problematic. I had standardized that one, and it's not going to be exactly 1 molar. It'll be some value. So we'll have to use the exact value that I give you in the lab. Okay. So there's the reaction for the formation constant. What we want to do is solubilize the silver as that we put in solution. We put in so much silver chloride in solution, then we solubilize it with ammonia. And then we titrate it with chloride ions. And the point at which we get the precipitate formed gives us a handle on the silver ion concentration. That's where the complex math comes in. All right, so, oh, there's another box. That's supposed to be all right. That's supposed to be, no, it's not gonna let me do it. That's supposed to be a double arrow. Now, we've got this reaction in that solution, but we also have this reaction that we're actually doing the titrating. Well, actually, let's put it this way. Let's write it as if it were solubility product. So now we've got silver chloride, solid, and silver ions, chloride ions. Now, we know what this one is. We know what the KSP is for this one. Okay. 1.6 times 10 to the minus 10, I think. I believe that's right. I'll correct it if I find different. But this is the one we don't know. Okay. So since both of these reactions are occurring at the same time in that solution, we can combine the two. All right. And if we do that, let's go ahead and do that. What do we get? I'm gonna write the whole thing out first, and then we'll deal with the potential cancel terms. Chloride plus complex ion. Okay. And that's going to be another, that's going to be a K value, whatever the KEQ is. And it's going to be this one times that one. But notice we have cancel terms, right? We can cancel this one with this one. And that gives us this one in the numerator and these two in the denominator. I think I've got that here. Yeah. So this one's going to be so let's write out that KEQ for now. All right. So we've got chloride ions. Let's see. Yeah, that's okay. Chloride ions and the complex ion. And in the denominator, we've got ammonia. Where? Okay. Here's the problem. That doesn't help us much because we still don't know what those values are. But if we take the KSP for this expression, right, and the KSP, let's go ahead and put it over here. Keep it organized. The KSP for silver chloride is simply the solubility product here. But we can substitute excuse me. All right, here's what I'm going to do. This looks unconventional, but it's necessary. If we keep the silver on this side and the silver here, right, we would expect them to cancel. But what we can do is is that right? Oh, okay. Now I'm gonna leave that for now. We're gonna take this one and combine this one with it. Because this one is here and this one is here. So the expression is going the KF times KSP, right? KEQ is actually KF times KSP, right? Because we combine these two equations, we have that one here, that one there. So this KEQ is going to be KF times KSP. So what's KSP equal to? Well, let's just multiply them together, right? So if we multiply them together, then we get this one times that one puts these two right here, right? Those two on top, and these two still on the bottom. Right? So that is this right here. Okay. I almost lost myself. Did I lose you? So far, so good. Okay. Well, I think I'm going about this the long way around. I'm going around the barn several times. We want to get KSP in here somewhere. So where's KSP? Well, KSP should be, if we say silver here is equal to KSP divided by chloride, like that, then we can substitute this one in here. That doesn't make any sense. So it didn't come out with the same equation. This one, that one. Or did I, wait a minute. KEQ. KSP over chloride should go down here, right in that position. But what happened to the silver? Silver's gone. Okay, so here's what we're doing. We're saying if this is equal to silver, then we can substitute that, not there. We can substitute this one right here. That way, we're still solving for KF. If we do it this way, then we're KEQ. That doesn't help us. But if we solve for KF, then we get the complex ion. And down here, we get ammonia squared times KSP divided by chloride. There we go. So if we can determine what these concentrations are, the KSP is a constant, we can determine what these are, then we can calculate the KF. Okay. We're going to use the value in here, 1.7 instead of 1.6. That's given right there in the middle. Okay. So that's supposed to have wide out. Maybe using a different version. Oh no. We got 3 flasks with 5 milliliters of silver nitrate solution. And we add 10 milliliters of 1 molar ammonia. Rather than the 5 molar, we're just going to stick with 1 molar because it'd take too long to do all those other titrations. And then we're going to bring the volume to 100 milliliters. So how you do that accurately, use a volumetric flask. So the volumetric flask, just like the big ones that you can use. And it's got a long neck on it with a mark on it. And once you get those solutions in there and fill it up with water to that mark, then you have your solution to be titrated. You just pour it into a 125 Erlenmeyer and titrate it. We're going to titrate it with the lights off. And we're going to use the Tyndall effect to detect precipitates. We'll shine this through, and that way it's easier to see with the dim lights, easier to see when the precipitate forms. Okay. So for building the ice table, building the ice table, we want an expression that accounts for all the species. So we don't want that KSP in there. We want the values that are associated with that KSP, which is silver times chloride. So we would put silver times chloride in here. Only there are two different chloride values. I'll explain that in just a second. So this has ammonia squared. And the KSP is silver times chloride. Okay, then we flip this up, right? The denominator of the denominator is the numerator. So now the chloride comes up here. So now in the denominator, we have ammonia squared times silver times chloride, and then this is the complex ion times chloride. Okay. So if we set up an ice table based upon that equation, I'm gonna have to erase some of this, sorry. Make room. Let's just do the whole thing. We're sort of working backwards. But if this is our equilibrium equation, then we can set up an equation that's based upon that. Right? On this side, we would have the complex ion. Well, actually, I don't need that, because this is a balanced equation. And chloride. And on the other side, we would have ammonia, right? 2 because it's squared. Then we'd have silver. I'm leaving out the aqueous part. Plus chloride on this side. Now we can set up an ice table based upon what we actually did in the experiment. All right. So here's the ice table. Silver, well, I got them switched here. Ammonia, silver, and chloride, and this is complex ion and chloride. All right, so when we start out in this example, we're going to use this expression to determine what our equilibrium values are. But it's more convenient to use absolute values at this time rather than concentrations. So it's not, strictly speaking, an ice table because we're not using concentrations. But if we take the initial amounts of silver, how much silver did we put in if we have 0.1 molar silver and put 5 mils in? 5 times 0.1 is 0.5 molar, millimoles. Right, that's where that one came from. 0.5 millimoles. Okay. The ammonia is 1 molar times 5 mils, which is 5 millimoles. Okay, that's what we put in. Chloride is, let's see, initial amount of chloride was 0.1 millimole. Hold on, let's go back. Set up the experiment. Okay. Okay. So what we're saying is that to reach that titration equilibrium, we put in 0.1 molar KCl at 1 mil. So we titrated that potassium chloride until we got the equilibrium position, and that's 0.1 molar potassium chloride times 1 mil. So we had 0.1 millimole. Initially. Okay. And we're saying that we started off with 0 here and 0 there. So what happens during the change? Well, we're going to use up all the silver. And the ratio is 1 to 2, so we're going to use up twice as much of this. So that's -1 millimoles of ammonia that we used up. But we're using up all the chloride. So that means that should be down here. -0.10. So this is 0, this is 0, and this is 4 millimole. Okay. So what happens to the change over here? Well, if we lose 1 millimole of ammonia here, the ratio is 2 of these gives you 2 of those. Or 1 of these gives you 1 of those. That would be a better way to go. 1 of these gives us plus 0.5 millimoles. And we lose 1 of these, get plus 0.1 millimole. Right? So now we have 0.5 millimole of this and 0.1 millimole of chloride in solution. Okay. Now that we have those values, we need to calculate the concentration. Okay. We have the absolute values, but the concentration we have to take into account is what's the final volume? Well, we started off with 100 milliliters, right? That our preparation was 100 milliliters, but we added some potassium chloride solution. How much did we add? We added 1 mil. So the final volume is 101 mils. So we divide each one of these by 101 milliliters. Millimoles divided by milliliters is molarity. Okay. And the values are given there. So those are the values that go back into the KF equation. This one. We set this one up just so that we could track all of our species. But this is the one that does the calculation, right? We have a silver value. Let's see. No, not this one. Erased. Oh, here it is. Here it is. Excuse me. We don't have the silver ion in here because it's canceled from both sides. We have the KSP, we have the chloride concentration, we have the ammonia concentration here, and we have the complex ion concentration there. Then you can calculate your value. The reason I put that in there in such detail is because now all you have to do is use the actual values that we use in the experiment and just plug them in. Right? So the math isn't quite as daunting. And then once you get that value, we just compare it with the given value. And since we're going to do 3 titrations, that gives you the opportunity, if you make a boo-boo on one of them, you can throw it out. That's called an outlier. And here's the calculation of 99.6% at 1 molar ammonia. 99.6% is ammonia, and the other 0.4% is ammonium. So if we're really sticklers, we would say whatever the concentration of ammonia that I give you, multiply it by 0.996, and that's your real value of ammonia. But the reaction is so complex in there, it could shift into more ammonia or less ammonia. So, you know, for our purposes, we'll just keep it there, whatever value I give you, like 1.016 or something like that, ammonia. I forget. I have to look on the bottle again. Any questions? This procedure doesn't have any pre-lab questions or post-lab questions. So that section is, I don't expect that section in your lab notebook or in your report. I just want to see the calculations. I want to see the answer and the comparison of the your value of KF with the accepted value of KF. And then we'll be good to go. Okay. All right. Well, I don't have anything else.